Welcome back to the course of Triple E324 Digital Signal Processing. Before heading for a break, we were discussing about the frequency domain analysis of LTI system, which is basically chapter 5 of focus. So we have covered this first section, and before we go for the second section, let's have a quick review so that we can refresh our basics, which will be used for the next upcoming sections. In time domain, we represent a system by its impulse response, which we will write as h of n, which is basically impulse response of a system. So in this course, we mostly focus on linear time invariant systems. So we will always assume that our system has this linearity and the time invariant property. So it's the impulse response system. If we take Fourier transform of this impulse response, so we get capital H of omega. So this thing is basically frequency response of our LTI system. Here omega is a variable which represents frequency. So, and if we focus on the formula of this frequency response, we know that h of omega is equal to summation h of k into e raised power minus j omega k, and k ranges from minus infinity to infinity. So here basically this h of k comes from its impulse response h of n. We basically define a variable k just to differentiate from the rotation. So we get this h of omega is equal to summation h of k into e raised power minus j omega k. Here this omega is basically frequency, this k is basically this k variable, and this j is a complex variable which we generally use as j. Sometimes we use I, sometimes we use j. So because this thing is complex, so the answer h of omega will obviously be complex. From complex theory, we know that if we have a complex variable, for example a plus jb, so we can also write this thing in polar form. So that comes out to be r e raised power j theta. So we have two variables r and theta. So for this h of omega, we will again have representation like r e raised power j theta. Basically r is the magnitude of this h of omega, so we represent that this thing is magnitude of h of omega, and e raised power j theta is the phase of h of omega, so we represent phase of h of omega. So this is basically frequency response of a linear time invariant system. One obvious question might be that how we get this equation. I mean, why we multiply h of n with e raised power minus j omega k to get the frequency response of that system. So we know that if we have a system which is represented by its impulse response, for example it's h of n, if we give input x of n to this system, then we will get output y of n. Mathematically we know that this output y of n is equal to input convolved with impulse response of the system, and this equation comes out to be summation k is equal to minus infinity to infinity h of k into x of n minus k. We can write this equation as k is equal to minus infinity to infinity x of k into h of n minus k. So both are same. if we assume that input to this system x of n is a complex exponential function. Complex exponential, it means e raised power j omega n. For amplitude we write a. So if this is input to the system, so what will be output? So output will be y of n is equal to summation h of k into a e raised power j omega n minus k. This is the cos k is equal to minus infinity to infinity. If we simplify this thing, so we get a summation k is equal to minus infinity to infinity h of k e raised power minus j omega k into e raised power j omega n. So here this term is defined as h of omega. So we can write this equation as a h of omega into e raised power j omega n. So if we rearrange, basically we can write a e raised power j omega n multiplied with h of omega, and this thing is equal to y of n. What this equation shows that if we give a complex exponential input to the system, this thing, so output will be like this, which is again a complex exponential function, but now it's multiplied by h of omega. So basically, if I give input a e raised power j omega to this system, which has impulse response h of n and its frequency response is h of omega, so output will be again a complex exponential function, but now it will be multiplied by h of omega, and this h of omega is called frequency response of a LTI system. And we can write this thing as a e raised power j omega n, because h of omega is a complex, so we can write this thing into polar form, and that will be j theta of omega. So it's magnitude of h of omega, and this thing is phase of h of omega. Okay, if h of omega magnitude is greater than 1, so it means that our output signal y of n will be amplified version of input signal, because it's greater than 1, so obviously y of n will be greater than the input, which is a e raised power j omega, so it will be amplified version of input. And if h of omega is less than 1, so y of n will be attenuated version of our input signal. So basically it's the role of magnitude of the frequency response of the system. So h of omega being a complex will have two parts. First will be its magnitude, which we represent of h of omega mod. The second will be theta of omega, which will be basically phase of this h of omega. So we call this magnitude response of our system, and this is called phase response of our system. We can also graphically represent this h of omega. Since it has two parts, so we will plot two parts. First part will be magnitude response. So on y-axis it will be h of omega mod, and x-axis will be omega, which is frequency. And we know that for discrete time signal, the maximum frequency is pi and the minimum frequency is 0. And we also know that for real time signals, because h of omega has a symmetric property, so for sake of completeness, we also plot here minus pi frequency. So basically when we always plot this magnitude response from minus pi to pi. Similarly, we have also phase response. So for this, again x-axis is omega, its range is minus pi to pi, middle point is 0, but y-axis is phase of h of omega, and we can also write it as theta of omega. Basically, these are two graphical representation of our frequency response of a system. So we have the frequency response of our system. Previously, we have calculated the Z-transform of our system, and which we have represented by h of z. Is there any way to calculate h of omega directly from z? Yes. And for this, what we do is that we replace z with e raised power j omega. And there is another condition, and that condition is that h of z should have unit circle within its region of convergence. If unit circle is within the region of convergence of this h of z, then by replacing z with e raised power j omega, we can directly calculate h of omega from h of z. We know that we can represent our LTI system using a constant coefficient difference equation, which we normally write as y of n is equal to minus summation k is equal to 1 to n a k y of n minus k plus summation cos k is equal to 0 to m b k x of n minus k. This is basically equation 3.3.7 of our textbook. Okay, so it's a difference equation representation of a LTI system. So here y of n is the output, which actually depends on the previous outputs and current and previous inputs. So if we take the Z transform of this equation, we get y of z is equal to minus summation k is equal to 1 to n a k y z into z raised power minus k plus k is equal to 0 to m b k x of z into z raised power minus k. Please go through this equation in chapter 3 and how we get this equation from this equation. We have seen this by using some properties of Z transform. We generally write capital Y and split bracket, so it will be like this. If we rearrange this equation, so we will get y of z is equal y of z into 1 plus summation k to 1 a k z raised power minus k, and it will be equal to k is equal to 0 to m b k z raised power minus k, and whole this term will be multiplied by x of z. We are just rearrange this equation, so we will get this, and if we divide y of z with x of z, so basically we have got it here. So what we will get, so this will be summation k is equal to 0 to m b k z raised power minus k divided by k is equal to 1 to n a k z raised power minus k. Actually, if we look at this equation, basically it's in the power of z raised power something. For example, if we know, we can write this 1 plus z minus 1 plus 2z minus 2 plus 4z minus 3 divided by it might be like 1 plus z minus 1 plus 4z minus 2 plus 5z minus 4. So it's an example. And from simple calculus, we also know that we can write this equation as, we can factorize the numerator and denominators. If we factorize, so we will get something like this: some factor multiplied by some factor multiplied by some factor. Similarly, this will be some factor multiplied by some factor multiplied by some factor, like this. So it means that this summation terms might be written in terms of multiplication of further factors. So knowing this, we can write this thing as multiplication of couple of factors. So this will be multiplication of k equal to 1 to m, and we can write it as 1 minus zk into z raised power minus 1, and similarly multiplication k is equal to 1 to m 1 minus pk z minus 1. So we will get this thing. So here this value zk and pk, these are actually coefficients. These zk will represent zeros and these pk will represent poles. Okay, and this thing is basically y of z over x of z, and it comes out to be equal to h of z. So it means that h of z is equal to multiplication of these terms divided by multiplication of terms. So here zk is zeros and pk is poles. Okay, if this Z transform has unit circle across its ROC, so we can get h of omega directly from this h of z. What we need to do is that simply insert z equal to e raised power j omega. So what we will get is that multiplication 1 minus zk with, actually this zk is coefficient, we are not going to replace this zk, is just a number. Here variable is this z minus 1, so it will be e raised power minus j omega, and divided by multiplication 1 minus pk, again pk is the coefficient, and we will replace z with e raised power j omega, and we will get e raised power minus j. So it will be frequency response of a LTI system. So we can directly get h of omega from h of z by simply replacing z with e raised power j omega. But condition is that this h of z should have unit circle within its region of convergence in ROC. If it doesn't have this unit circle within its ROC, then we can't get the h of omega directly from h of z. Okay, for any system we know that output y of n is equal to x of n convolution with h of n. So basically in time domain the output is equal to input convolved with the impulse response of the system, and in z domain this convolution becomes multiplication. So we write it x of z multiplication with h of z. Similarly, in frequency domain, y of omega is also equal to x of omega multiplied by h of omega. So in time domain, the multiplication, and in z or frequency domain, so in time domain we have convolution, and in z or frequency domain we get multiplication. Another thing is the pole and zeros. We know that suppose we have this z plane, cross x-axis we have real of z, and cross y-axis we have imaginary of z, and we plot a unit circle which is basically a distance of 1, and if we plot zeros we represent with circle, and if we plot pole we represent with cross. To get values of poles and zeros, what we do is that suppose we have this h of c, it will have some terms here on numerator and some terms of denominator. To get zeros we put this numerator equal to 0 and we get values of z. So all these values of z will represent to zeros of the system, and if we put this denominator equal to 0, again we get the values of z, but this time these values of z will be poles of the system. So knowing these all basic concepts, now we can proceed to the next sections. So go for the next videos.